Okay, thank you, Venki, for the brief introduction. Just to save some bandwidth, I'm going to switch off my video. Once again, I welcome you all to the second webinar of this NVH series. So today, we are going to start with some background on acoustics, why it is important, what are the various ways to look at the acoustic challenges that we face. Then we will move on to various solution methods, especially the numerical methods like finite element method, boundary element method, relay method, and other things. And we'll also discuss about what is the need to have these different methods, when to use what methods, those kind of things. Then we will move on to the pure pressure acoustics, where we talk about only the fluid medium where the acoustics wave propagate without having a consideration of any structure or the other physics. Then we will slowly move on to how do we study the wave propagation as well as the acoustic noise generations from the structure. So we handle them in the vibroacoustics. Considering the time limit, we will briefly talk about viscothermal acoustics, room acoustics, and the diffuse sound acoustics, but I'm sure I will give you some feel for it and when it will become applicable and a necessity as we move on. Then we will, as promised in the last webinar, we will talk about the multiphysics acoustic simulation. So when we are designing a product or system which involves multiple physics, like flow is generating the noise, the flow is generating a fluctuating pressure, that fluctuating pressure acting on the structure, which kind of generating the noise, then the noise radiates through the air, those kind of things. Or the electric motors where the electromagnetic force make the structure to vibrate, that in turn radiate the noise, those kind of applications. Then my colleague Alex will talk about, okay, once we have the noise acoustic pressure fluctuation signal, either from the simulation or from the test measurement, how do we look at those signals and how do we gain useful insight to make design decisions? And also he will talk about how do we combine the information that is coming from the simulation and some of the information coming from the experimental measurements. Now we want to combine these two things to perceive the sound that is going to come out from the real world system. Okay? Then we will summarize and we are open for the discussion. So noise, vibration, and hoarseness is the common nomenclature for the audible sound between 20 to 2000 kilohertz. As noise standards are becoming stringent across all industries, also a significant factor in making buying decisions. So it is important to ensure that your product meets the industry noise standards and also performing acoustically better than the competitors. Commonly, the poor acoustic performance of the product means to the consumers or the buyers, it's a poor quality product. It doesn't matter whether the sound perception coming out from the product really impacts the performance of the product or not. So the consumers perceive a product which is having a poor acoustic performance as a poor quality product. So considering the number of product variants introduced in the markets in today, the successful product development is driven by resource and time. The market gives leeway for neither. The number one challenge is producing a robust and reliable product in a least time and resource consuming way. Considering this, the acoustic performance not only perceived in terms of the product quality. Today, when we are designing a product or a system for any system, there was a time, a decade back, there were silos. People were doing the structural analysis, stress analysis, material selection, manufacturing, crossworthiness, and things like that. Today, we are talking about designing a system and optimizing a system with a multidisciplinary optimization point of view. It means that when we start the concept and when we go for the detailed design, the features and the materials and the dimension not only need to be optimized for the stress or the durability, we need to co-think about all the performance measures of the product. In that way, the NVH becomes one of the integral part of the multidisciplinary design optimization for any product. Especially when we are looking at the industrial products, machineries, or the wind turbine, this also becomes the part of sustainability drive in many industries. So generally, noise is produced from two sources. The first source is due to the turbulences in the flow. Across all industry, this happens. The other source of noise generation is the vibration of mechanical structural elements. These vibrations start radiating the noise, then these noise propagate through the air and unperceived by the nearby human beings or even the animals, sea life creatures, and so on. So today webinar, we will focus more related to structural vibration or any device where the fluid flow is not predominant. There can be a fluid flow like a silencer or muffler, but that flow speed is relatively very small. It has a little influence on the acoustic performance of the system. So majorly we will focus on the structural mechanical related vibration or the stagnant flow acoustic devices. In the next webinar of this three-part webinar series, we will focus more on the flow related acoustics. All right. Now let's look at the solution methods. So when we are start thinking about the acoustic study, broadly we can classify our insights or the information that we need to look for into two different domains. So some of the problems where we need to look at how the acoustic field distribution, either in terms of the acoustic velocity or acoustic pressure in a time domain. Something like we are using some sensors or the MEMS device, which is going to start radiating the ultrasonic waves, or there is an impact that is happening on the structure that is trying to vibrate the structure. We need to focus more in terms of the time domain. There are other kind of a scenario. If you are talking about the IC engine noise or the electric motor noise, the operation is going to happen for hours of time duration. So when we are start looking at the data in terms of time domain, it does not make much sense. We will have a huge amount of data. In those kind of steady state dynamic situations, we would prefer to look at the acoustic pressure or the sound power in terms of the frequency, which is directly related with RPM. When the motor runs at 1000 RPM, what happens? When the motor runs at 2000 RPM, what happens? So these are all the two broad classifications. So again, this is the way we want to visualize. Then if you want to find these solutions, there are many numerical techniques. In time domain, we can use a finite element method, or in theory, all these methods can be used in both time domain and frequency domain. So what I'm talking today is about what Ansys as a simulation provider offers in our suite of simulation tools. For time domain, Ansys offers finite element method based solvers and spectral element method based solvers. For frequency domain, we offer finite element method and statistical energy method and ERP and the boundary element method. We will talk more about this as we go forward. First, I want to throw a question. What is the need for having so many types of solvers? Why don't we live with one single solver that address all the requirements? As we know in engineering, there is no silver bullet that will kill all the challenges. Okay, depending on what we need to kill, we need to use a different weapons. The same scenario here. So there, in order to understand when to use what, we need to understand some fundamental requirements in terms of meshing to predict any acoustic field distribution. So the acoustic is nothing but kind of waves that is propagating through the medium. Depending on at what frequency the waves move, the wavelength become an important factor. Okay, at low frequency, the wavelength is kind of a long. At high frequency, when it propagates, the wavelength become shorter. In order to predict the wave motion, the wave moves, assume that it moves in the sine form. In order to capture this sine form, we need to have so much of divisions or elements to capture one sine wave. If we use many element divisions to capture one sine wave, or you can think in terms of many elements within the one wavelength, then we can capture the sign fluctuations more correctly than using less number of elements. And as a rule of thumb, it is known in the industry, if we are using the linear elements, we need to use 12 elements per wavelength, and quadratic elements 6 elements per wavelength. But again, like in the structural analysis, if there is a zone where there is a discontinuity of the acoustic impedance, or there is a sudden change in the flow behavior, then we need to use the refined mesh around that region to capture the complex acoustic field fine. So why it is important, right? Let's imagine we have a room of size 7 meter by 5 meter by 2 meter. There are some noise devices. This is a living room. Assume that we want to understand how the acoustic field distribution is. Okay, let's assume if you are playing a music or song from the speaker, if those frequency of those music sound is somewhere around 1000 kilohertz, if we are interested in analyzing up to 1000 kilohertz in the air, we can calculate the wavelength as 0.3 meter. And if you are using 6 elements per wavelength, then the element size becomes something like 0.05 meter. So if you start splitting this room by 0.05, we will get around 380,000 elements. Okay, this K stands for 1,000 elements. This is kind of a manageable. Now, the human ears are having audible range up to 20,000 hertz. If you want to predict the acoustic field within the room correctly up to 20,000 kilohertz, at 20,000 kilohertz, the wavelength become 0.01 meter. Okay, and if you are start using 6 elements this is supposed to be 0.0137. This is not 346. This is supposed to be 0.0137. Then the element size will become so small. If you are start splitting this room by this much small element size, we will end up having 3.1 billion of elements. Okay, so solving this model with 3.1 billion of elements is though theoretically possible, and in the practical workstations or even in the HPC clusters, this become challenge. So that is the reason many times in acoustics, these different methods are found to be many practical in certain frequency range. The FEA is found to be very much suitable for the low frequency range, where we will have a very distinct resonance mode, so that we can individually study what is the effect of individual modes. Maybe up to 1000 hertz of frequency. Then there is a mid-frequency range where um, the, the resonance of the systems are relatively closely spaced, where again, as I said, as we are going for the high frequency, the element count become very high. That's where we typically use the boundary element method. As we go towards the very high frequency range, something like more than 5,000 or 10,000 hertz, where the system will not show any distinct mode. It is very, all the modes will look almost similar. So very difficult to identify which are all the individual resonances. In those region, we will use the SCAE approach. Okay? In terms of the finite element method, let's say we want to study this is a car cabin, we want to study when there is a speaker or how is the engine noise get distributed inside the car cabin. We need to mesh the entire air domain that's filled inside the car cabin. Similarly, if you want to study how this vehicle is going to radiate the noise outside to the roadside passengers, we need to mesh the air domain around it. That's the way we approach finite element method. In boundary element method, there is no need to mesh the air domain, either interior or exterior. We need to mesh only the boundaries so that the number of elements are going to come down. It doesn't mean that the boundary element method can be used to solve any range of problem, because in the finite element method, the resulting matrix are going to be a sparse matrix. So there are so many zero terms which we can eliminate while doing the calculation. But in boundary element method, it finally results in a fully populated matrix. Though we are having small number of elements, the matrix size is still going to be a challenge to solving that. Okay, so that's why we can't use neither the boundary element method at all places. The statistical energy approach is further simplified approach at the high frequency range, which give the overall system behavior. We don't even mesh the boundaries. We kind of split the entire core as the number of panels. We will study only in terms of the panels, rather looking at the local mode shapes of the structure. Okay, this is why we need to use different techniques to solve different range of acoustic problem. Again, commonly any type of acoustic problem can be classified into three categories. The first category is we want to study the noise that is radiated by the product exterior to the product. Typically, any engine casing which is vibrating, this is going to radiate the noise outside the engine casing that is of interest. A speeding car, due to the airflow around it, it is going to generate a noise. Or a electric motor which is operating at certain RPM, it is going to radiate the noise outside, right? There is another class of problem. They are called as an interior problem or cavity problem. Something like we want to understand how is the acoustic performance or acoustic experience of the car cabin when we are sitting, the passenger experience, or like a room. So we are studying inside the boundaries. Okay. There are another class of problem where both the interior and exterior, both is of our interest. If you take a speaker with a box, when we have a tweeter or the tuning ports, the acoustic waves which are going to come out depends on this enclosure volume and the enclosure design. So the output performance depends on both the interior cavity acoustics as well as the exterior acoustics. The typical applications are the speaker box or the guitar. The box that we have here at the front, that really determines the acoustic performance of the guitar. There are these kind of problems where we need to consider both interior and exterior acoustics. Typically car, yes, both the in-cabin experience and the noise radiated outside the car, both are important, but they can be kind of separated. They can be studied in a independent way. But for certain products, we cannot separate them out. We need to study them in a tightly coupled way, right? Okay. Having discussed about the solution methods, let's move on to the pressure acoustics. So when we are talking about a machine, let's assume you have a large shop floor where there are many different machines sitting. You want to study the acoustic experience. So what we are generally interested is at different places in our domain, at different time, how is the acoustic pressure variation? That's all is our interest. At different spatial location, at different time point, how is the acoustic pressure variation? To find this, basically what we are going to solve is the wave equation. So in one dimensional, this is a well-known wave equation which has a spatial component as well as the time component. The unknown we are going to solve for is the acoustic pressure, right? In terms of the 3D, the delta operator becomes not just the x, it's going to be function of x, y, and z that we are going to solve. The same time domain equation, when we transform into the frequency domain, we call that as a Helmholtz equations. So when we solve this, we will get the pressure as function of x, y, z. That's what we are going to solve in a finite element method. So when we, having known this equation, what we are going to solve, the way we solve this equation in a numerical way is different in the boundary element method and the finite element method. In the boundary element method, we do the boundary integral using the Gaussian theorem to find what is the pressure as a function of frequency at various points. As I mentioned earlier, in Ansys, we have a boundary element method only in the frequency domain, not in the time domain. So we solve pressure as a function of frequency at various spatial location. In the finite element method, we again solve the same equation, but we write them using the weighted residual method. In this, we will incorporate various boundary condition and the material properties. So when we solve that, this is the fundamental difference between the boundary element method and finite element method in terms of the numerical technique, right? Let's do a deep dive on the acoustics using the linear wave equation. One of the classical example is solving the interior flow problems like acoustic muffler, where the noise attenuation happens due to the expansion of the volume of the flow or the car cabin, and even the outlet, depending on different outlet shape, the noise which is coming out can be different. Those kind of scenarios can be solved. There are well-known analytical formulas to calculate the transmission loss of a muffler, but the problem is that this all the theoretical equation works up to certain frequency range where the wave can propagate as a plane wave. There are certain frequencies where the waves are no longer propagating as a plane wave. In such a situation, the theory breaks up. Okay, the theory will not anymore follow what is we are seeing in the measurement. So that is where the numerical technique like finite element method and boundary element method become very useful beyond certain frequencies where the analytical formulas predict to fail, whereas the numerical techniques will help to predict the transmission loss of the muffler. So it is not only the predicting the transmission loss. We can use Ansys tools to optimize the muffler design for the maximum transmission loss. We can try to change the shape from circular to elliptical. We can try to introduce the micro perforated tubes and other stuff and see how they are improving the transmission loss of the mufflers at desired frequency range. There are certain cases, though, as I mentioned, the flow velocity through the silencer is relatively very small. There are certain applications where the flow velocity is having the impact on the transmission loss. In those kind of situations, we can use, we can import the velocity field of the flow through a CFD simulation into Ansys Mechanical, or Ansys Mechanical itself is having a convective wave solver, okay, so which can solve for both the flow field, flow pressure, as well as for the acoustic pressure. So again, remember that when we are when I talk to different engineers who are newly entering into acoustic, they are often confused with the acoustic pressure or the pressure that we typically use in the structural analysis, right? The acoustic wave is nothing but the oscillation of the pressure above and below the mean pressure. Normally, the normal atmospheric pressure is approximately 101 kilopascal. But if you look at this small fluctuation is what we call it as acoustic pressure. So the traffic noise that we hear, that is typically around 85 dB. To produce this 85 dB, the small fluctuation of 0.1 Pascal is enough. Okay, and if you hear the jet noise are considered to be a very loud noise, something around 140. To produce 140 dB of sound pressure level, the pressure fluctuation required is just 100 Pascal, which is very small even you compare to the normal atmospheric pressure. So it is remember that the acoustic pressure is a small fluctuation above the mean pressure. It is not the total pressure, right? That is something you need to keep it in mind. And when we are talking about this muffler or any sound attenuation devices, the micro perforated tubes are quite common. If you want to mesh those small holes, we end up having a lot of mesh and the solution time will increase. Instead of doing that, we can use the admittance matrix, which kind of relates what's the velocity and the pressure across this micro perforated tube, so that we can use this analytical input that will eliminate the need for meshing these small holes. We can represent that as a regular elements. Still, we can get accurate results. There are a lot of sound attenuation porous materials like foams and screens being used across the industry. So wide range of material model is required to model these complex sound attenuating materials. Okay? So Ansys offers equivalent fluid models to capture the porous materials, and also Ansys can predict the variation of the material properties as a function of temperature, also as a function of static pressure. Ansys offer wide range of material models to model the foam type of materials used in the mufflers or used in the genset, so that you can study when we put the mic somewhere away from the genset, when we are using the foam in the genset, how is the acoustic pressure sound level, or without the foam, how it is sound level, or when we are having the complete the tailpipe system, there would be a great reduction in the temperature as well as the sound level. Okay, so we can study as a function of temperature in the exhaust system how the sound attenuation is happening. And also Ansys do offer the piezoelectric material models, which are typically used in the civil industry. Here I will show just quick examples and the validation due to the time limitation. I hope this will give you a feel for what kind of applications you can use Ansys acoustic tools. This is a triple panel layer used in the windows and the ceiling floors kind of a stuff. There is aluminum plates, and in between air, how the transmission loss is. Then if you are introducing the foam in between those two layers, how the transmission loss is going to improve. And moreover, if you have a rigid porous material, how the absorption coefficient, and if you have a piezoelectric screen type of materials, and we can calculate the absorption coefficient from Ansys. So these kind of panels and the soundproofing materials are used while designing the studio acoustics or the sound in sound protection chamber inside the industrial. Okay, these examples and the validations are available with us. If anybody is working on the similar application, you can reach out to us. And also there is a lot of theory and the examples available as a part of Ansys documentation. You can also look at depending on what type of application that you are working with. Having the concept that we have discussed so far, HR tractors have been using Ansys suite of tools to maximize the transmission loss of their tractor mufflers. They could reduce their design time for a muffler design from 20 weeks to 8 weeks, At the same time, by reducing the overhead cost by 40%. Okay, this also meant to them by reducing the cycle time, and they reduced the time to market in producing high performance mufflers for the tractor application. The same technology that we spoke about, the pressure acoustics or the cavity acoustics, is being used in the aerospace industry, like designing the Helmholtz resonator, or to study the combustion instability in the rocket motors and so on. Probably whatever they are trying to do with the test can be virtually simulated. It's not only in the aerospace. All the acoustic concepts that we are talking is equally applicable, whether the medium is air or water, right? In the underwater acoustics, scattering is an important phenomena for the defense and reconnaissance applications. So Ansys can be used to predict the scattering pattern and to predict the target strength. Here is the benchmark against a verification study to show that the Ansys scattering predictions are very close to the benchmark requirement by the industry. Right? Having spoke about the pure wave propagation in the fluid media, now let's go on to the next stage of vibroacoustic, where the structure and fluid are going to interact with each other. We have seen earlier, for only the fluid medium, this is the equation we were solving. But when we want to study if a vibrating structure like this motor casing is vibrating, this is going to radiate the noise, then we need to couple both the structural dynamic equation and the fluid equation. Okay? The blue color terms are the additional loads that exchange between the fluid domain and the structural domain, right? So when we write this in a matrix form, we end up having a unsymmetric equation, right? So this is not a symmetric equation anymore. So when we are solving any vibroacoustic problem, the matrix becomes non-symmetric, so that the solution time and the storage time for any vibroacoustic problem is really large. The way we handle that, we model the air domain, which is going to have only the pressure degrees of freedom. Then we model the structural domain, the vibrating structure, which is, let's say if it is a solid, it's going to have 3 degrees of freedom in the 3 translational direction. There would be one layer of element that is shown here that will have both the structural and fluid degrees of freedom, so that the velocity of the structure is translated in terms of the pressure. That's what we are seeing here. That's how any coupled vibroacoustic problem that is working, this is how we are solving this problem. To start with this, to give you a feel, the pulsating sphere is the classical problem in a vibroacoustic industry. So the sphere is pulsating. There are analytical equations to calculate what is the pressure at any location, at any frequency, if you know what is the velocity at which this is the sphere is pulsating, and what is the frequency at which the sphere is pulsating. As you can see here, there are results at different locations at different frequency. Ansys predicts in many low frequency range exactly with that of analytical results. Now, what is the main learning from this is the structural velocity is the one which is governing the acoustic pressure. In this case, the pulsating sphere, the velocity at every point is same. But as we are going for a higher modes of the sphere vibration, the velocity is not constant at every point. So the velocity is different at different points in different direction. That's where it becomes complex. We need to go for a FEA solution. The same concept can be applied in a plate vibrating in a room or the motor vibrating. So the velocity at different point is same. That is going to radiate the noise, or that's going to produce the fluctuating pressure that is responsible for the noise. The same concept, if you have a speaker system, the speaker is supplied with electrical voltage, so the speaker diaphragm vibrates with some velocity. that vibration is producing the noise around the air domain. So once we know what is the pressure at different spatial locations at different frequencies, we can calculate the response. It means whether when you are playing a music, it is going to give you a smooth response at all the frequencies, or suddenly some frequency noise goes up and goes down, and the directivity of the speaker. Okay, what is the beam range in which you can hear a better performance for this noise? Those kind of things can be studied. If you have any machineries, for this case, you assume an engine casing. There is a crankshaft which is rotating because of the unbalance or whatever reasons. There is a vibration through the bearings. The vibration in the crankshaft get transmitted to the casing. Then the casing ball is vibrating with the velocity. This is nothing but this velocity is going to excite the air around it, similar to a sphere. The other case, it was a sphere, but in this case, the surface is not a sphere, the casing. There it was a constant velocity, but here different points are having a different velocity. Then it's going to excite. Then we can see at various frequencies how much noise it is radiating, what's the directivity, in which direction it is going on. And many companies are using this concept to study the noise due to the structural vibration of the system. And also this can be used to design the in-cabin acoustic performance. Let us assume the panels are vibrating. If you put a mic here, we will see some resonance peaks. Some peaks are due to the structural resonance. Some peaks are due to the fluid resonance. Say, for example, if you want to reduce the noise at this particular frequency, this is due to the structural mode. We need to introduce some damping mechanism that will reduce the vibration. But if you want to reduce the noise level at this frequency, this is a fluid dominated mode. If you are introducing any structural damping mechanism like a rubber sheet or something, this peak will not come down. Instead, we need to introduce a acoustic damping mechanism, introducing something like a foam or a sound absorbing material and so on. So this can be used to study and choose a suitable type of noise treatment. Again, when we are designing the acoustic enclosure for the genset or different machineries, stone crushing machineries and so on, typical question we have is, okay, how thick foam should be, what should be the porosity of the foam? And those kind of simulations can be done even considering the vibration behavior of the panels in addition to the porous acoustic foam. And we can study when we use different types of foam, how the SPL distribution across frequency and overall noise level. Well, now I mentioned so far what we spoke about is the finite element method, but when we are using the boundary element method to study these kind of applications, I mentioned the boundary element method is available only in the frequency domain and not in the time domain. But let us imagine you have a golf bat. When you are hitting the ball with a golf cart, the sound perception is very important because the game of golf itself is considered as a executive level or luxury sport. So the every minute details is important here. So if you want, when they hit, what is the sound they are going to perceive? This cannot be predicted in the frequency domain. We need to do a time domain to predict this impact. So we do a time domain analysis first. Then we will use Ansys FFT to transfer the time domain data to a frequency domain data. So now we will get what is the surface velocity of the bat at every frequency. Then we can carry out the acoustic analysis in frequency domain. So this velocity information is coming from the structural simulation. It can even come from the measurement. So if it is measured using some instruments, we can feed it to the Ansys LS Dyna, and we can use boundary element method to calculate the sound pressure level around the object. Here is another example of a ball impacting a plate. So here the objective is when this impacts, the plate start vibrating. We want to see how the noise is perceived when we put some mic somewhere away from that. To optimize the sound perception, different materials are tried for this plate. The first one you are seeing here is, I'm not sure. Can you hear? Can somebody confirm? Ravi, can you
Yes,
hear?
Santosh. Yes, Santosh, we can hear you.
No, I mean, can you hear the sound?
Yeah, Santosh, we cannot hear your sound.
No,
If you
sir,
can
no.
just include the audio.
Audio is not
Just,
coming.
yeah, just give me a minute, yeah? Come back. Let's see why it is.
Santosh, looks like we need to activate one option while sharing the, like initially when you started sharing the screen, there was an option to optimize for motion and video.
Yes, I did that. Let me stop and share again. Audible now?
Yes.
Okay, all right. Let me back. Okay, so here the objective is to choose the suitable material for this impacting plate so that the sound perception is good. The first one that is tried with is with titanium alloy. I hope we can. Ravi, can you hear now?
Yes, Santosh.
Okay, good. And then this is the sound when the ball impacts the zinc plate. The same when we use pine wood, right? So there are certain situations where we want a louder sound. There are certain situations where we want kind of smooth and muffled sound. So depending on the requirement, the simulation like this will help you to optimize your material and the structural vibration frequencies and so on. Okay, here is another application where the time domain simulation of acoustic field is very helpful. When we are using the piezoelectric sensor or the ultrasound waves for medical scanning and other purposes, the transient domain simulation would be very helpful to visualize the beam patterns. Here is another application of a reverse parking sensor. From the sensor, we send out the ultrasound waves. When it hits any obstacle, the wave will get reflected, and the reflected wave is received back on the sensor. So depending on the time taken between the sound wave to travel, hit any obstacle and come back, it is possible to calculate what is the distance between the rear of the car and the obstacle next. Those kind of applications can be studied. This slashing is generally not directly related to sound, but I have seen in automotive and aerospace industry, the NVH group is normally handling this and looking at this aspect. Using the same vibroacoustic equation that we discussed, by adding another term which is responsible for the slashing, it is possible to study the slashing of the fluid inside a fuel tank or any process equipments. It is not only just the slashing mode. Because of this fluid slashing, the vibration shapes and the stress on the structure is going to change. Those will impact the durability and life of the structural components as well. Those can also be studied using the same technique. And this is also useful to study the earthquake surveillance of the liquid containing structures like high-rise water tanks, or when we transmit liquids through the track, then there will be a lot of random vibration, excitation that is coming to the fluid. The fluid adds additional slashing load to the structure, and even under the random vibration. So those kind of things are also possible using this vibroacoustic studies. And in industry, especially for the underwater application, when we have any impeller or ship turbines which are inside the water, their wet natural frequencies are much lower compared to when we test those propellers in a lab in a air environment, because the water is heavy, which adds some extra mass to the structure. So the same vibroacoustic technique can be used to study the wet frequencies of the structure, which are partially or fully immersed inside the water or any heavy fluid, right? And when the acoustic waves are propagating through a small channels, typically that we see in the speakers, in our cell phones, or the microphones or the hearing aids, where when these flow go through a small channel, there will be due to the high shearing effect of the fluid, a lot of heat generated, where viscosity plays an important role in making sure the performance range of this kind of miniature devices good over a large frequency range. So to do that, in addition to the regular wave equation that we have seen in the beginning, we have to introduce additional terms that will take care of the viscosity and the heating effects. For that, in Ansys, we have many semi-empirical models, as well as the linear full Navier-Stokes equation that can be used to study the acoustics of micro devices like hearing aids, microphone, inkjet printers, and so on. Here is an example. Acticon is a hearing aid device design and developer from Australia. They have been using Ansys tools. Using Ansys simulation for their product development, they could see up to 75% free time, because whatever the time they were spending earlier to create the test scenarios and the physical testing is kind of reduced by the simulation, that free up their engineering team to do other innovative work. Similarly, when we are designing the building acoustics, especially defining the partition and what should be the sound absorbance coefficients for these partition panels are very important. But as the building size are really large, doing a detailed finite or boundary element study is going to be quite expensive. So we use the energy-based method to study the room acoustics. So when we introduce a partition, how much sound is reduced from one room to other room, those kind of studies can be done. The diffuse sound acoustics is something important when the acoustic waves are very random. Typical application you can imagine is during the launch vehicle firing, there is a lot of sound coming out because of the exhaust. This sound can go and impact the outer body of the launch vehicle, which carry the satellite and other very delicate instruments. So that will make those delicate instruments to vibrate and fail. In order to study those kind of scenarios, we don't know exactly at what direction the waves are coming in to hit the structure. So we assume that the waves are coming at a random phase angle from all the direction and hitting the structure. Then we will study how much structure is vibrating, how much noise is going inside the capsules where the satellites are sitting, those kind of applications, right? And moving on to multiphysics application, like if we take the car, in car, the majority of the noise is due to two components. One is the road tire interaction noise, and another one is the wind noise. So if you want to study the wind noise, first we need to start with the fluid flow simulation in a transient domain to compute the fluctuation of the pressure on the car body. This fluctuating pressure will make this fluctuating pressure will make the glasses to vibrate. In turn, the glass will start radiating the noise inside the cabin. So the entire workflow starts with, we need to solve for a full-scale turbulent transient CFD analysis to see how the pressure fluctuation on the glass. Then we kind of export those data after doing a Fourier transform. So finally, we will get frequency versus pressure on the glass. Then we carry out the vibration analysis. Then these vibration will start propagating the noise, as we have seen in the previous slides. Okay? This is a one. The electrical machinery NVH is a big area. Now the electrification is happening across many places. Even the conventional powertrains are replaced by electrical powertrain these days. In this, the noise become a very important criteria, because many of these electrical machines produce very high frequency noise, right? So the typical workflow starts like this. We first start with doing a magnetic field simulation, where we will calculate what is the electromagnetic forces being produced between the stator and rotor. Then we transform those forces in a frequency domain to the structural vibration, where we will predict what's the vibration velocity of the structure. Then those vibrating velocity is imposed on the acoustic domain to calculate the sound radiated by the vibrating motor at various RPM at various frequency. The typical workflow look like this. We start with Ansys Maxwell for the electromagnetic simulation, Ansys Mechanical for vibroacoustic simulation using finite element method. Then finally, we use Ansys Sound tool to really perceive the sound and analyze the sound order analysis and so on. My colleague Alex will talk more about this. So though I have shown the workflow using Ansys Mechanical, the same process can be done using the boundary element method in Ansys LS-DYNA. Start with Maxwell, do the structural vibration analysis, either in Ansys Mechanical or LS-DYNA implicit, then carry out the acoustic analysis using boundary element method instead of using finite element method. So the step one, magnetic force prediction. And then we transfer this magnetic force prediction from time domain to frequency domain through a Fourier transform. Then apply this on the tooths of the motor. Then we start modeling the structural component of the drivetrain that can include the casing, gearbox, and all the enclosures and so on. There can be any misalignments or transmission loss between the gear trains. Those can be modeled using a multi-body simulation. Then we can transform all the electromagnetic forces to this complete assembly, and we will predict the vibration velocities. Once we know the vibration velocity, those can be applied as an input for the acoustic simulation. Then we know the acoustic pressure distribution around the motor. At various RPM and at various frequencies, we can predict the directivity plot of those motors. This is kind of involve detailed acoustic simulation considering the impedance of the air around the vibrating structure. There is another quick way of doing that. That is, we can do that using the Rayleigh integral method. Here, we don't really go for a detailed modeling of the acoustic domain. We just solve just the structural harmonic analysis. So from this, we know what is the velocity at different points of the structure. Then we assume that as an equivalent source, the knowing what is the normal velocity at every point, it is possible to predict what will be the sound pressure at any point somewhere away from this structure using this Rayleigh integral technique. We can just do this equivalent radiated power and equivalent radiated power calculation without even getting into a detailed acoustic study. This will be useful for a quick and comparative study between two designs. Not only this, Ansys offers many type of post-processing tools that will help you to actually mimic whatever you are measuring in the real world environment. Okay, you can put various, like when you put mics at the various location and measure the directivity and the sound pressure level, we can create a far field mics in Ansys at various location, collect the data and produce the similar directivity plots or the sound intensity plots that is coming from any measurements. Okay, when we are doing this kind of multi-physics acoustic simulation, it is possible to connect all type of analysis required for those multi-physics simulation, starting from geometry, your fluid flow analysis, thermal, stress. So all these analyses are interconnected. Here, to optimize this design space or to do any design of experiments, design sensitivity studies, it is possible to parameterize any of the parameters across this physics, starting from geometry, material, boundary conditions used in fluid flow or thermal or for the vibration. And we can, with a single mouse click, it will update all the analysis and give you a sensitivity accounting all different physics together, right? So when we are doing the multi-physics simulation across various RPMs, finally we get the waterfall plot. Then as we are revving up the engine, we can export the information of the pressure data from Ansys simulation to Ansys sound, where we can actually start listening this sound coming out of this engine as we ramp up the RPM. When we are doing this kind of analysis, there are situations where we may not do a simulation at certain aspects. We just have a measurement data, but with that measurement data alone, we can do a lot of insight and analysis in optimizing the design of the sound behavior of the system. Now I would hand it over to my colleague Alex Lee, who will talk about more on the signal analysis, combining the sound signal from the simulation and test and so on. Alex Lee, over to you.
Yeah, thank you, Santosh. Yeah, so Jamie, let me just try to explain a little more about how the Ansys sound product can help you to deep analyze the sound. So first, you will already see these slides on the previous webinar already mentioned by our product owner. Ansys sound, it's a kind of analyze platform for all the acoustic sound and also vibrations, whatever it comes from your measurement or comes from any kind of NVH simulation workflow. You can try to listen to your recording or try to create some audible sound from your simulation results. So you can start with audible sound samples, try to listen to it, analyze it, compare it, and optimize the final acoustic performance of your product. Next, please. So here, for example, if we look at a simple EXL product, we will normally handle from a vehicle. So it's kind of a mix. We also can call it a three-in-one powertrain systems. It's was contain a electric motor, a reducer with some gears, and some electronic control modular. So here we can listen to a sound from a record. Next, please. Yeah. I don't know if we can play it.
I'm trying to play that. Can you hear Alex now?
Yes. So you will find it's a really noisy recording in real like test bench. It's recorded from of EXL product. We can easily try to extract any parts of the sound from by Ansys sound like what you are playing with Photoshop, and listen to each component. Like here, yeah, please play it. Okay, a little bit noise because it's only the harmonics from the electric motor. And also here's the, yeah, play. Yes, this is the order from the gear. So this is coming from the mesh, gear meshing. And also you can also listen to the PWM noise like in the right. So this is a more kind of static, high frequency noise. So you can easily separate and understand the noise from which component contributes to the overall noise easily by you can just modify it like what you are playing with a Photoshop, extract any part from a recording and listen to it. Even you can try to also modify it. So first you already know the Ansys sound. It's really strong tools help you to understand your recordings. Then if you try to work with your simulation results, so next, please. Yes, we will introduce interesting tools. It's called Sound Composer. It's a very interesting tools coming of Ansys Sound, which can help you to combine the sources from whatever it's coming from any part in your product, from simulation or from task, and try to combine it together with the accurate or with the real control parameter, and also you can try to consider the transfer function into it. Next, please. Okay, so help you to understand the sound at the receiver point. So it's the overall you need to what you will receive at your customer receiver. So for example, we still look at the EXL. So we will first on the top left, we can easily listen to a simulation. So here. Okay, so this is the simulation, how it looks like. And also you can easily extract the background noise from your measurements, just as I showed before. Maybe you don't need to play it, play this part. And also you can Okay, this is a background noise. Yeah, no problem. Yes. Yeah. So you can find we can try to handle over the recording like here. It's another example from the Vacuum Climber. We can just extract order and keep the recorded flowing noise at there. And maybe we can combine with a new motor noise coming from a simulation together. And altogether, we combine the simulation and result together. We can also try to consider transfer function like mentioned in the left button, to understand how the sound will be propagate from the sources to the receiver point. And also we can consider the operation condition for each sources. So like here, it's simple examples. We try to simulate a sound. So this is, first you can play this one. This is recorded sound. Yeah. So this is a recorded background noise of a vehicle when speed up. And we can try to simulate another kind of condition when it's closed down. Okay, so this is a totally virtual new scenario we created based on a recorded the data, which is speed up, and we record and we generate a new kind of virtual scenario. It goes down for you to try to analyze another scenario. Maybe you are not recorded. So combined with all this together, we can easily try to combine your task and a simulation result together and consider all the facts will infect the final perception of your sound. So here is an example of a sound coming from the EXL I just mentioned. So in the left side, it's a recorded noise. You will see there are several orders in the measurement. Some are coming from your motor, some are coming from your gears. And we can try to easily remove the original orders coming from your original EXL product. And maybe we can try to replace it with another product, another EXL models. And next, please. Yes. So this is another product, another EXL we can put into this vehicle. Again, without make a real physical prototype. We can just do it in a virtual ways to put into a new EXL coming from a simulation or coming from your bench test. And you can first listen to it, and you will see there's several different on the color maps. And with Ansys Sound, we can also help you to evaluate the difference from these two products at system levels, not only by listening to it, but also offer some kind of very reliable cycle cost indicators. Like listed below, you can try to do all the trackings to understand the specific orders contribute to the overall levels. And also you can track the tonal prominence ratio of specific orders, help you to understand the emergency levels of these tones. Like here, you will find there's a little bit different between the measurement and prediction. In the measurement, we can find around 6,000 RPM. We can find the gear meshing orders are really audible. And in the right, you will find the order noise can be also audible around like 2,050 RPMs, kind of thing. 2,500. Yes. Next, please. So what you can think more, it's not only replace your product by a simulation result, like I just showed you. You can also try to combine your test results at different levels, like at very beginning, maybe you just have some data from a test bench and component level. You can also try to understand into a system level with Ansys Sound in a virtual way. And also you can try to, next please. You can also, like I show you, you can also change the operation condition. You can use your recorded speed up result to simulate what it can be heard in a coast down condition. And also you can try to consider the difference between transfer functions, like you can put the same product into two kind of vehicles, but just changing the transfer function. You will understand how the transfer function will influence the overall sound quality at receiver points. So you can try to consider all these factors will impact the overall sound perception. Also, you can try to analyze them separately and understand your sound and try to optimize your final sound qualities by change any part of these factors in the Ansys sound. Next, please. So here is what I'm just trying to show. It's you will already get a general idea about how Ansys Sound can help you to get insight into your test results and try to listen to your simulation results and begin an audible analysis on your simulation result and combine with test result to understand them in a really system level without build up a real physical prototype. I believe this kind of workflow can help you to very quickly understand your performance, NVH performance of your product in a very early design phases. So saving the cost on NVH prototypes and avoid this kind of defects in a very early stage. So I believe the benefits is really obvious here. So that's the part I will share today on the Ansys Sound part. So I will give the ball back to Santosh.
Thank you, Alex. As we have seen, Ansys acoustic solution offering include pre and post-processing tools to prepare your models, visualize the acoustic result, combine simulation and test measurement results to perceive the sound signature of the real-world systems. And also, Ansys offers wide range of powerful, accurate solvers with high-performance computing enabled. And also with the gold standard individual physics solvers, the workflow that Ansys offers today is enabling you multi-physics acoustic simulation for electric vehicles or flow-induced vibrations and so on. So as a whole, for acoustic studies, Ansys offer accurate, fast, robust, flexible, and easy to use simulation and sound analysis workflows. By using Ansys acoustic solution as part of the product design and development workflow, help to minimize time-consuming, costly build and test design iteration, and help you to stay ahead and sustain in introducing cutting-edge acoustic designs in your product. With this, the technical session is over, but I want